Good afternoon and welcome to this lesson dedicated to polymeric materials, which is presented in the frame of the class Materials and Their Properties of the Federal University of ABC. I am Professor Mathieu Champeau and this lesson has been prepared with the help of Daniel Heinz. So here we are going to present basic information about polymers. So first of all, we will learn what is a polymer. After that, we will present how synthetic polymers are obtained. So it will focus on polymerization. Then we will present the different levels to describe the polymer structure. And finally, we will present crystallinity and crystals in polymers. So first of all, what is a polymer? In this slide, you can see that different products that are made of polymers. On the left part of the slide, all these products are made from synthetic polymers. So there is a plastic bottle made of polyethylene terephthalate, some pipes made of polyvinyl chloride, bags, plastic bags made of polyethylene, and styrofoam made of polystyrene. So we call synthetic polymers all the polymers that are produced in industry. And it is opposed to natural polymers. So you have some example on the right part of the slide. For example, wood, cotton, proteins, or latex, they are all natural polymers, so polymeric structure that we find in nature. So if we compare the properties of polymers with metals and ceramics, you can see that they present some advantages. For example, they have a very low density, so they are lighter than metals and ceramics. They have a low melting point. However, they have a low elastic modulus. They are very reactive with other chemical species. They are ductile, and we can also find brittle types, so either ductile or brittle. And they are cheap, flexible, and most of them are electrical insulating. So what is a polymer? Here you can see a polymeric chain. So it is a sequence of atoms, as you can see. In this case, we have carbon atoms that are bonded together through covalent bonds. And apart from this polymeric backbone, you can see other atoms that are present. So let's see another representation of this polymeric chain, where all the atoms are represented. So here, as we described, we have the polymeric backbone, on which all these carbon atoms are linked by covalent bond, and a part of them, the hydrogen. So it is an example. Hydrogen can be other atoms or other molecular groups. And in order to describe this very, very long chain of atoms, we can use a repeating unit, the representation of a repeating unit. Because in fact, you can see that this repeating unit is repeated many times to create this long chain of polymer. So we will say that polymers are defined as macromolecules, which means a huge molecule composed of several small repeating units linked together by covalent bonds. And how do synthetic polymers are obtained or synthesized? So we will call this chemical reaction polymerization. So we start with a monomer. So in that case, for example, ethylene. You can see that ethylene is composed of 2 carbon atoms with a double bond between these 2 carbon atoms. and each carbon atom is linked to 2 hydrogen. We use catalyst or initiator, we use pressure or temperature to perform this polymerization. And in that case, in the case of ethylene, we will use a catalyst, and this catalyst is represented by this letter R. And you may see this little dot at the side of R, which is in fact an electron. So here we have a radical. And this radical is very reactive, and it will react with this molecule, this monomer of ethylene. In fact, this double bond of ethylene is composed of electron, and one electron from this double bond will react with this electron from the catalyst in order to create a new covalent bond between the catalyst and a carbon atom. Whereas the second electron of this double bond will go to this other carbon. That's why you can see this representation of this electron with this small dot on the structure written on the right. After that, this new structure, since it has a radical, it is also highly reactive, so it will react with another monomer of ethylene. So you should imagine that you have a mixture with ethylene, with catalyst, and so each time a radical will be created in this reaction, this radical will tend to react with another double bond present in another monomer. And so you can see that this reaction is occurring. In that case, we have two monomers that has been integrated to this beginning of polymeric chains. And this reaction will be repeated n times. So we will have n cycles, n reactions. At the end of this reaction, at the end of this polymerization process, we will end up with a polymer. And so here you can see the structure of the obtained polymer. The polymer that is obtained from the monomer ethylene is called polyethylene. And so we will write a notation, which is PE for polyethylene. In order to describe the chemical structure of a polymer, you can see that we only represent the repeating unit of polymer within brackets, showing the covalent bond that is linking this repeating unit to the next ones. And in order to say and to represent that in this growing chain, in this polymeric chain, we have n repeating units because the reaction occurred n times. So we write it with these small indices. So it is very important to represent a polymer. We only represent a repeating unit within brackets with these small indices. Bon, this was an example for the polymerization of ethylene to obtain polyethylene. And of course, depending on the monomers that we will use, we will obtain different polymers. So it exists another polymer that instead of having 4 hydrogens, has 4 fluorine. And so performing the polymerization of this monomer, we obtain the polytetrafluoroethylene, PTFE, that we also call commonly Teflon. So you can see that in that case, the repeating unit is different. So after the process of polymerization, we obtain a lot of macromolecules, so long molecules. And we used to represent these long molecules like spaghetti. So you should imagine that the samples that you obtain is made of various polymeric chains like spaghetti. And as we said, we have covalent bonds between the repetitive units within a polymer chain, but we also have secondary bonds, such as van der Waals forces, between the chains or between some parts of one polymeric chain. So here are some definitions. So we presented what is a macromolecule. It is a long molecule formed by at least 100 atoms. We describe what is a polymer. It is a macromolecule formed by several repeating units linked together by covalent bonds. Repeating units are simplest group present in a polymer that repeats itself. And monomer is the initial molecule that results in a polymer after polymerization. After that, we can introduce a polymerization degree. So we saw that when we represent the chemical structure of a polymer, we use this notation and we write this small index, which is n. And in fact, n is the polymerization degree. It is the number of repeating units in the polymer molecule. Then we can introduce other definitions. Oligomer, which is a polymer with low polymerization degree. So we will describe it after. Homopolymer. So up to now, we only introduced a chemical structure of homopolymer, because homopolymer is a polymer with only one type of repeating unit. But if we start using two different monomers for the polymerization, so we will end up with different repeating units. So in this case, we will say that we obtain a copolymer. So it is a polymer with more than one type of repeating unit. Here you have some copolymer organization, molecular organization of a copolymer with a repeating unit A represented in black, repeating unit B represented in red. And you can see that you can have different sequences of this A and B unit. So it can be random, it can be alternated, you can have block of repeating unit A, block of repeating unit B, or you can have one long chain of repeating unit B with some branched chain of repeating unit A. So you can see that you can have different architectures, and this is controlled during the polymerization process. So during the polymerization process, we control the architecture of the polymers, and also we control the polymerization degree. So now let's focus a little bit more about on polymerization. So polymerization, as we said, is a process that monomers go through in order to form polymers. In this process, monomers react between themselves, forming long sequences of repeating units that we call polymers. And in this class, we will describe two main mechanisms of polymerization, which are called chain growth and step growth polymerization. So let's start with chain growth polymerization, that is also called addition polymerization. This polymerization mechanism follows three stages. And in fact, we have already described part of this polymerization process when we describe the example of the polymerization of polyethylene. So the first stage of this mechanism is the initiation. So free radicals are formed by breaking a double or triple bond by using an initiator, which is represented in blue with the letter R, in the monomers. So we already presented the reaction of this initiator, in that case that possesses a radical that will react with the double bond, and we have a transfer of an electron to the carbon on the right part of the monomer. Once we have the initiator that reacted with the first monomer, we go through the propagation stage. So here in the propagation stage, we have new generated free radicals that interact with new monomers. So the radical that is formed will react with another monomer. This other one monomer will bear a radical, which will react with another monomer, and so on. So we can represent that we have the reaction of this species that will react with N monomer, and we will end up with this long chain, with this polymer. And this the final stage in chain growth polymerization is termination. So in termination, it is the stage where the chain growth stops for different reasons. And one of the reasons for these chains to stop growing is that we have two radicals that will meet each other in the polymerization mixture and will create covalent bonds. So two radicals find each other and end the polymerization, because once these two radicals find each other, they create this covalent bond, and we don't have anymore any radical on the growing chain of the polymer. So no more reaction. So to summarize, in chain growth polymerization, we have three stages: initiation, propagation, and termination. So on that slide, we present common chain growth polymers. On the left part of the slide, you can see different monomers that have different chemical structures, but all of them have one thing in common. They have a double bond, carbon-carbon double bond. And as we explained, this double bond is highly reactive with a radical coming from an initiator or catalyst. So depending on the monomer that we use for the polymerization, we explained that we obtained different polymer with different chemical structure. So for example, the first example is with the monomer methyl methacrylate. After polymerization, we have polymethyl methacrylates, or PMMA. So this polymer is used to produce the window that you can find in airplanes. So it is a rigid polymer. With styrene, the monomer styrene, as you can see, it passes a phenyl ring. After polymerization of styrene, we obtain polystyrene. That is the polymer that is used to create these glasses, but they are not made of ceramic or glass. They are made of polystyrene, of a polymer. Using ethylene, we obtain polyethylene, as we saw, so PE, that is used, for example, to create polymeric films. The propylene is polymerized into polypropylene, PP, and is used to create some recipients for cosmetic or domestic usages. And finally, the last example, the polymer polyvinyl chloride is used to create such kind of pipes, PVC. So we presented chain growth polymerization, and the second polymerization technique is step growth polymerization, which is also called condensation polymerization. So this polymerization mechanism happens between bifunctional or multifunctional monomers. So what does it mean, bifunctional or multifunctional monomers? It is monomers that possess two or more functional groups that are reactive. So let's take the example below. You have here presented the reaction between diacid and diamine. So in the diacid, you can see that this molecule possesses two carboxylic acids, and diamine possesses two amine groups that are reactive. And we have the reaction of one carboxylic acid with one amine that react together and create an amide link. So during this reaction, we have also the release of a small molecule, and in that case, the release of a molecule of water. So you can imagine that each group of each bifunctional or multifunctional monomers will react, and this will enable from each part, each side, each group, functional group of the monomer to react with another monomer of the other kind. So the diacid will react with two monomers that have an amide, and this will permit the growth of the chain. Okay. On the example on the right part, we have another reaction. We have a monomer, which is a diacid, that contains two carboxylic acids with another monomers, which is diol, so it possesses two alkyl groups. And there is a chemical reaction between the carboxylic acid and the alkyl groups to create an ester link, ester bond. And during this reaction, there is also the release of a small molecule of water. So in that case, we obtain a polyester. So in this step growth polymerization, there are no well-defined stages. All the reactions are happening at the same time, and the chains are growing from the two sides of the polymeric chains. In the case of chain growth polymerization, only one side of the chains was growing, the one where we could find the radical. In that case, no, we have the reaction of both sides of the chain, where we have a chemical function that is reactive. So here you have some example of common step growth polymers. So for example, starting with a phenol and formaldehyde, you will form a phenol formaldehyde resin that we commonly call bakelite, which is a very strong and rigid resin. If you polymerize adipic acid that contain a carboxylic acid, two carboxylic acid groups with a diamine, which is the example that we saw previously, so you create polyamide, or we call it also nylon. So depending on the structure of each monomer, so it is a 6,6, nylon 6,6, or it can take different numbers depending on the structure of the monomer that has been used. Then the other example is the reaction of dimethyl terephthalate with ethylene glycol. to create polyethylene terephthalate, PET, that is used to produce the plastic bottle. And finally, the phosgene and bisphenol A enable to produce polycarbonate, which is a rigid and transparent polymer that is used to create, for example, this protection for policemen. So up to now, we presented what is a polymer. We introduced how they are obtained, so through polymerization. And we saw that there are two common polymerization mechanisms, which are chain growth polymerization and step growth polymerization. So now we are going to define the polymer structure, so to see the classification for this polymer structure. So the first thing that we saw is that the polymer structure can be defined by its chemistry. So what is the repeating unit composition? Then we are going to describe the size of these polymeric chains, which is very important because many properties of polymer depend on the size of the polymeric chains. So it is one of the most important features of a polymer, which is the polymer length, or we will call it the molecular weight. So the molecular weight of the repeating unit is calculated, and it is written M. So it is the sum of the molecular weight of each atom. And if we have N number of repeating units, so we can define the molecular weight of the polymeric chain as MW. It is a notation for the molecular weight, MW, which is equal to N times the molecular weight of the repeating units. And so, depending on the polymerization conditions and how we control the polymerization step, we can control the size of the polymeric chains. So we can control the molecular weight. The low molecular weight polymers, as represented on the left, mean that we have short chains. We can separate them easily. They are too short to entangle, so they won't entangle one with another, and so they will behave independently. So you can think about the image of a bowl of rice. On the contrary, if we have high molecular weight polymer, we have long chains, and all of these chains are entangled. So it is the image of a spaghetti, bowl of spaghetti. And the chains, in that case, do not easily move independently. Okay, it is difficult to select only one spaghetti. You have many of them that will come together because they are entangled. So talking a little bit more about the molecular weight, if you think about simple molecules, they have a low molecular weight. For example, water, you can calculate the molecular weight of water, which is equal to 18 grams per mole, or other simple molecule will have low molecular weight. On the contrary, talking about polymeric molecules, we will have high molecular weight molecules. So depending on the value of the molecular weight, we will range this polymer, we will classify them. So if the molecular weight is lower than 1000 grams per mole, we will say that we have an oligomer. If it is between 1000 and 10,000 grams per mole, we have a low molecular weight polymers. So for example, the film made of polyethylene are created using chains of polyethylene that have a molecular weight that is low, that is classified as a low molecular weight. So then we have the medium molecular weight polymers, high molecular weight polymers, and when the number is higher than 1 billion gram per mole, we call them ultra high molecular weight polymers. So for example, the bulletproof body armor are also obtained with polyethylene, like it is the case for this polymeric film. But in that case, we will select the polyethylene that have ultra high molecular weight in order to give this mechanical resistance that is needed for this application. So the commodities polymers that are used in many functional applications, they have a molecular weight between 15,000 to 500,000 gram per mole. So after the polymerization process, we will obtain many polymeric chains, and probably all of them won't have the same molecular weight. It is very difficult, even controlling very well the polymerization process, to have a unique molecular weight for all the polymeric chains. And so in that case, we will say that we have a molecular weight distribution. So the polymer molecular weight is not a specific value, but a distribution of sizes. And so in order to describe the molecular weight in a sample, we will use the average molecular weight. So we have two ways to description of this average molecular weight. We have the number average molecular weight, which is written MN, and the weight average molecular weight, which is MW. So first of all, let's see this graphic that represents the number or the fraction of the total number of chains that possess a specific molecular weight. So you have this Gaussian that represents this distribution. In that case, what we will do is that we will separate this distribution in a small range of molecular weight. So we will have a series of size ranges, and we will determine what is the fraction of the total number of chains that possess this mean molecular weight. Okay, so in each range there is a mean molecular weight. So this mean molecular weight for this fraction E, we will write it ME. So from that, let's come back to the definition of the number average molecular weight, MN. So it is equal to the sum of the number of chains, NE, that possess the molecular weight, ME, divided by the total number of chains that you have in your sample. I can also say that this value is equal to the sum of the fraction of the number of chains that possess the molecular weight ME times the molecular weight ME. So here we are talking in terms of number of chains having a specific molecular weight. Okay. On the other side, we have the weight average molecular weight, MW, which is equal, in fact, to the weight fraction of chains with the molecular weight, ME, in our sample, times the molecular weight, ME. So it deals with the weight the weight fraction of chains with a specific molecular weight. So we defined two ways of describing the average molecular weight in order to describe the sample, the size of the chains in the sample. And it is very important to know the molecular weight of the chains, because many of the properties of the polymer are dependent on this parameter. For example, in that case, it is represented the evolution of the melting temperature of the polymer as a function of the molecular weight. And you can see that up to a certain value of molecular weight, you have an increase of the melting temperature with the molecular weights. Okay, up to high molecular weight, a certain number of molecular weight, upon which the melting temperature does not increase anymore and reach the constant value of 145 degrees C. So we describe the chemistry, the molecular weight of the polymer. Now let's talk about the shape or molecular conformation. So the polymeric chains should not be considered as straight. In fact, the chain bonds can rotate and bend in 3 dimensions. So let's see the first scheme, number A, which represents 3 atoms of carbon. So you can see the chemical bond, the covalent bond between the first 2 atoms of carbon. And let's consider where will be placed in space this 3rd atom of carbon. And you can see that this atom of carbon won't be placed anywhere in space. In fact, there is a specific angle of 109 degrees between one chemical bond between the 2 first atoms and the chemical bond between the 2nd and 3rd atoms. But respecting this rule of the angle between the bond, the 3rd atoms of carbon will be placed in this cone, anywhere in this cone. And so, if now we consider a chain with a higher number of atoms, we will have many atoms that will respect the rule of the angle between 2 bonds, but on which the carbon atoms will be placed on this cone. And so you can see that many atoms can have different positions, and this produces chain bending or twisting. We don't have anymore, probably we won't have a linear chain. So, and these atoms can move. It is a dynamic, it is a dynamic position. And so, for example, depending on the temperature at which the sample is submitted, so we will give some energy to the sample, and we will favor this movement of the atom. And so the conformation of the chain will evolve in time. So conformation is defined as the 3-dimensional spatial arrangement of atoms or groups that is changed under the effect of thermal motion, but doesn't involve breaking of chemical bonds. So the conformation of a polymeric chain can change in time without breaking the chemical bonds. And so we will see that some of the mechanical and thermal properties of polymers depend on the arrangement of the chains and the possibility of the chains to change their conformation upon stress or temperature. Oh, sorry. Okay. So, we saw the conformation. We represented the conformation and the bending and twisting of a single polymeric chain with few atoms. But if we represent a huge polymeric chain with a high molecular weight, so we will have such a structure with some parts that will entangle. But you should imagine that this polymeric chain is not isolated, so it is within a mixture with other polymeric chains, so all the polymeric chains will be entangled. And the change of conformation will depend on the chemical groups that are present on the chain. So large group present on the backbone of the polymeric chain will make it more rigid and more difficult to get this rotation of the polymeric chain, of the atom in the polymeric chain. And so we have the influence of the chemical group on the molecular conformation. So we described the chemistry, the molecular weight, and the shape of the polymeric chains. Now let's talk about the structure of polymers. So we can have different kinds of polymeric chain structures. First of all, we have the linear structure. So you can see that you have long chains that are totally linear and independent. And in that case, you can have a high packing of these chains. They can come close one to another. And this can facilitate what we will see after. It can facilitate their crystallization. The second class of polymeric chain structure is the branched structure. So in that case, you have side branch chains that are covalently linked to the main chain, the main backbone. So you have branched chains. In that case, the packing of these chains due to this branched is very difficult, it's more complicated, and so the density of these polymers is lower than their equivalent linear chains. So if you have the same polymer with the same chemical structure, but if one is linear and one is branched, so the branched one will have a lower density than the linear one. After that, we have cross-linked polymers. So we have a covalent bond between adjacent chains. These covalent bonds are created generally by adding other atoms or other small molecules with the polymer, and there is a chemical reaction that permits the formation of these covalent bonds between the polymeric chains and these atoms or molecules. These bridges are called cross-linking, okay? And the number of cross-linking points of cross-linking bridges is directly depending on the number of atoms or small molecules that have been introduced in the polymer. And so these kind of structures are found in rubbers, elastomers. If we increase a lot the number of cross-linking in a cross-linked polymer, it will result in a network. So in fact, both cross-linked and network structures are only different or differentiated due to the number of cross-linkings that you have in the structure. The network can also be obtained by another way, which is making the polymerization from monomers that have at least 3 reactive sites, so 3 functional groups that are able to react during polymerization. And so in that case, it will result in a rigid structure, in a rigid polymer. And so, for example, it is the case of epoxy resins, bakelite. So depending on the chain structure that we have, we will have different thermomechanical behavior of our polymers. So thermomechanical behavior is the mechanical behavior of the polymer depending on the temperature. So if we have linear or branched polymers, they will fall into the category of thermoplastics. So what is a thermoplastic? It is a polymer that can be melted several times and reshaped. So I can melt this polymer, I can shape this polymer during the polymer processing, and after that, after the use of the product, I can melt it again and give him another shape. So, so we say that we can recycle these polymers. So thermoplastics can be recycled. It is a case of polyethylene, polypropylene, polystyrene, polyamide, polyethylene terephthalate. All of them are thermoplastics. But we also have another category called thermosetting, which means that the polymer can only be shaped during initial fabrication, and after that, it cannot be melted and reshaped. So it is the case when we have cross-linking in the polymer structure, like in cross-linked or network polymer structure. Why? The cross-linking are found during the initial fabrication. So as we said, we have a chemical reaction between occurring during this process between the chains and small molecules. And once we have covalent bonds between the adjacent chains, this cannot be broken by temperature. This polymer cannot be melted. To break this covalent bond, in fact, we need to burn the polymer, and so it cannot be used anymore, right? So in that case, with thermosetting, due to the presence of this cross-linking bond, we cannot melt the polymer and reshape it. So it is the case of epoxy resin, bakelite, rubbers, and so on. So let's take another example to illustrate the impact of the chain structure on the properties of the polymer. Let's take the example of polyethylene. So here are represented 3 kinds of polyethylene. So the first one is low density polyethylene, LDPE. And you can see that this polymer has a branched structure. This branched polyethylene is used to create the polymeric films. Then we have the linear low density polyethylene. So you can see that even if the name says that it is linear, we have very short side chains. But we call it linear low density polyethylene. And finally, we have a high density polyethylene. In that case, we have long chains of polyethylene. So the molecular weight of these chains is higher, and we don't have these short side branched chains So all of them are used to create different products because in fact they have different properties. So you can see that there is an increase of the thermal of the melting temperature of polyethylene depending on the chain structure. So it increased from LDPE, LLDPE, and HDPE. The density is also increasing when we decrease the size of the side branch and by increasing the molecular weight. And the tensile strength is also increasing. And so you have the same chemical structure, but the chain structure is different, and so the properties of the polymer is different, and so they are used for different purposes, for different products. So now let's talk about polymer configuration or isomeric states. So when we talk about molecular configuration, we are talking about the arrangement of repetitive units along the polymer backbone, which cannot be changed without breaking the chemical bonds. So let's consider this repeating unit that possess a group R, a side group R. Either you can have a sequence of these repeating units having an alternate order of this side group R. And in that case, we will talk about head to tail configuration. Either the group R will be adjacent in these two repeating units. So in that case, we will say that we have a head-to-head configuration. And so configuration means that we have the same atoms, but in different sequences along the polymer chain. So now let's see the different stereoisomerism that we can find in the configuration head to tail. So in that case, we have different, the stereoisomerism is the different spatial arrangement in head to tail configuration. So let's take the example of polypropylene. So polypropylene has similar repetitive units as polyethylene, but instead of having 4 hydrogen groups, we have 1 methyl group that is represented in that case with this yellow ball, yellow atom. And polypropylene can have 3 sequences, 3 spatial arrangements of these atoms. So when the R groups, when the yellow balls are located on the same side of the chains, which is the case on the first representation, we will say that we have an isotactic polymer. When these groups, these yellow balls, are at alternated sides, we will say that we have a syndiotactic polymer. And when there is a random order from one side to another of the chains, so we will have an atactic polymer. So in that case, in the case of polypropylene, we have isotactic polypropylene, syndiotactic polypropylene, or atactic polypropylene. And these 3 polymers, even if they have the same chemical groups and the same chemical composition, have different properties and so different uses. Okay, so let's summarize. We describe the polymer structure from the chemistry of the repeating units, the molecular weight, the shape of these molecules, so the conformation. Then we describe the different structures that we can find and the configuration in polymers. Now let's talk about the crystallinity in polymers. So since we are working here with a material that is composed of molecules and not of atoms, so the description of the crystals in polymers is a little bit more complex than in metals or ceramics. But we can describe the state of matter in a polymer structure using two extreme cases. So on the right part of the screen, you have the representation of a crystalline polymer. In a crystalline polymer, we would have all the chains, all the segments of all the chains of the sample within forming a crystal. So this would be a 100% crystalline polymers. This structure does not exist. We won't find in nature or in our synthetic polymers, we won't find a 100% crystalline polymer. On the other extreme, we have the amorphous polymers. So in that case, in these polymers that we actually can find, all the chains are in an amorphous structure. In fact, we don't have long range order of these chains. So for example, in polystyrene, we have an amorphous structure. All the chains are in amorphous state. And in between of these extreme cases, we have semi-crystalline polymers. And you can see that in semi-crystalline polymers, we have some region where the chains are highly ordered, they form crystals, and parts of the chains and of the sample that is in amorphous region. There is no specific order in this region. So we will find either amorphous polymers or semi-crystalline polymers. And to describe how the chains are organized in semi-crystalline polymers, we can use the chain folded model. So this chain folded model represents semi-crystalline polymers as composed of crystallites, which is crystals, dispersed in an amorphous matrix. So if we have a look to these crystallites, this model represents the crystallites as formed by a chain of polymer folded many times in another way to form lamella. So these lamella are composed and can be composed of different parts of different polymeric chains. And they have a thickness ranging from 10 to 20 nanometers thickness, and a size that is approximately 10 micrometer long. But if we take a polymer, we melt it, and we cool it. If the chain can organized, so it will form a semi-crystalline polymers, and it will form 3D structures that have spherical shapes. And these 3D structures are called spherulites. And it is a much more realistic description of semi-crystalline polymers than the chain folded model. So these spherulites are formed by lamella that radiate from the center to the external part of spherical shape. So when we cool or melted polymer, we have a nucleation site, which is represented here at the center of the spherulites. And from these nucleation sites, we will have different lamellas that will grow in a spherical way. And this lamella will branch. And between this lamella, we will find amorphous portion. So it is part of the chains or some polymeric chains that are not ordered. And so it forms the amorphous part of the semi-crystalline polymer. And so thinking about the growing of these spherulites, so it starts from the center and it goes to the external part of these spherical structures. And so it will continue to grow up to a point that it meets another spherulite that is growing on the side. When they begin to touch and to meet each other, it hinders their growing. And we have the formation of an interspherulitic boundary. So it is kind of similar of what we saw in metals and ceramics when we describe the growing of grains and the and the grain boundaries. So here you have a representation on the left part of the slide of the growing of spherulites during crystallization. So you have during the crystallization and at the end of crystallization where you can observe the interspherulitic boundary. Okay, so we described the crystals and semi-crystalline polymers. But you should know that the polymer crystallinity is influenced by various parameters, and various parameters that we described before when we talked about the polymer structure. So, for example, if we have a polymer with a chemical structure that favor intermolecular forces between two chains, the crystals, the formation of crystal will be facilitated. So it is the case of nylon. Oh, sorry. It is the case of nylon. You can see that the structure of nylon right here, the chemical structure. And so you have hydrogen bonds that is formed between one chain and another. So in nylon, the formation of crystal is facilitated. Then talking about a configuration of polymers, the chains with a regular structure will crystallize more easily than others. So it is the case, for example, of isotactic and syndiotactic polymers that will crystallize, whereas atactic polymers, some of atactic polymers won't be able to crystallize. Then it will also depend on the processing parameters. If we have a process in which we allow the polymer to cool from the molten state more slowly, so the chain will be able to move and to rearrange slowly in order to form these crystals. On the contrary, if we have a molten polymer and we cool it very quickly, the chains won't have time to move and rearrange in order to form the crystals, and it will result in a very small amount of crystals in our semi-crystalline polymer. So we have, you can see that we have different parameters that can favor the polymer crystallinity. On the contrary, some parameters hinder the crystallinity of polymers. So for example, polymers that possess large side groups, such as the phenyl groups in polystyrene, will hinder the possibility to crystallize. So that's why polystyrene is amorphous. The branched chain also hinders the crystallization. So, then the last parameter that is presented here is a case of a quick cooling from the molten state that we already described. So in case of metals and ceramics, we were able to easily describe the different crystal structure that we obtained. In the case of polymers, we can also describe these crystalline structures, but they are much more complex. And in fact, in that case, it won't be the atom, the individual atom that will be placed in the different position of the crystal structures. Instead of that, it will be the molecular chains. Okay, so you can see the representation on the left part of the slide, and you can see the structure formed in this case, in this polymer. We represent the chains that are forming this arrangement, this crystal. And now talking about the impact of crystallinity, we say that the molecular weight influences the mechanical properties of polymers, but also the crystallinity is really important. And crystallinity also depends on the molecular weight of the polymers. And so in the case of polyethylene that is represented on this graph, you can see that depending both on the crystallinity and the molecular weight of the chains, we will have either a liquid or wax, which can be more soft or more tough, or if you increase the molecular weight and increase the crystallinity, you will have a plastic. So for the same molecular weight, depending on the crystallinity degree of the polymer, which is the portion of the polymer that is within the crystal and not in the amorphous region. So if the crystallinity increases for the same molecular weight, it will result in a more brittle polymer. So this graph represents this influence of both the molecular weight, and the crystallinity of a polymer on mechanical properties. Okay, so in this class, we learned what is a polymer, and we saw some applications of polymers. We presented two kinds of polymerization: chain growth polymerization and step growth polymerization. We described molecular characteristics and structure of polymers. And finally, we saw crystals in polymers. We said that we have amorphous polymers and also semi-crystalline polymers. Thank you very much. If you have any doubt about this class, you can send your question on TGE, or you can wait for our session in Wednesday at 5 on Zoom. Thank you very much.